Today we have a very special event, and I think there is no better opportunity for me to talk to you a little bit about QueRC. Many of you probably don't know what does QueRC stand for. So it stands for QuakeCoRE Emerging Researchers Chapter. We are a group of students and early career researchers working in earthquake-related topics. We have 4 chapters, one in Auckland, one in Wellington, one in Dunedin, and another one in Christchurch. The Christchurch chapter, which is organizing this event, is based at the University of Canterbury, and we have at the moment more than 50 members, mostly postgraduate students and postdocs. Our members work across many disciplines: engineering, law, sociology, earth science, etc. And our main goal is to promote networking and knowledge sharing between our members and the community, such as industry and other bodies like city councils, etc. This is the program for today. I hope that you people in person enjoy a little bit of tea and coffee. After that introduction, I would like to also thank our QueRC mentor, Jeff Rogers. It's an impressive work that he works with us, and thanks, Jeff, for your patience. Also, this is a joint event with Aurecon and Beca. Thanks especially to Arsalan and Nico for putting a lot of time in the last couple of months organizing this event. Also, thank you to the QuakeCoRE admin team and the rest of QueRC executives organizing the event. We will have an introduction by Arsalan and Nico. Then we will move on to the business, presentations by our 4 speakers. And then we won't have questions at the end of each presentation, but we will have a large group of questions at the end. And we want this event to be more like a discussion than just listening to presentation. We want the audience, not only those in person, but especially the large number on Zoom, to ask many questions. And we are going to do that through Slido. So if you are not familiar with Slido, you can go to this website with this passcode, or otherwise you can scan the QR code displayed on the screen. Questions with more votes are going to be asked to the speakers. After we are done with the questions, we estimate around 5 p.m., we will ask you to join us for a little bit more of discussion and some refreshments at the staff club. The staff club or University of Canterbury club is 10 to 15 minutes from here. Many people will from university know the way, so I hope that all of you join us rather than rushing off. But we appreciate that you may have some other commitments. Okay, I think that's all from me, and I would like to welcome at the stage Arsalan and Nico, please.
Thanks, everyone. The idea behind this panel discussion was actually inspired by a an interview that the late Professor Tampole had in 2003 with the Earthquake Engineering Research Institute, in which when, sorry, just the other way around. And when Robert Reiterman from ERI asked the late Professor Tampole what he thinks about the next generation of structural design and designers, and he responded, and I'm quoting here, "I am not very confident with respect to the appeal to the younger generation of designers of the use of these unconventional yet simple engineering features I have advocated. Challenges in the development of ever more powerful software relevant to analysis and promising greater accuracy and resolutions of complexity seem to magnetize the younger generation more than the global aspects of the design strategies." And then he finished his response with a quote from Nietzsche saying, "Science is science, that is the mastery of knowledge, only to the extent to which, beside techniques, it is also philosophy." Almost 20 years has passed, and these words are still as relevant, if it's not more. And since 2003, a lot has happened on this front, and Niku is going to tell us more where we are now.
Since 2003, Professor Pauly interviewed, the role of the software to understanding the structural performance increased dramatically. These days, with the advance of the software, structure engineer could design more complicated structure, and it is great. This is awesome. But there's one question is that there's a lots of different software, Space Gas, ETABS, SABS, Perform 3D, Romoco, OpenSys. And there's one question is that which one of them we should use it? And is all of them is the same usage, same advantage and disadvantage? There's lots of questions here. And even when you choose one of them, there's another question is that which type of analysis we should do? Go for the equivalent static or response analysis, or need to go to the nonlinear pushover, or need to do the time history analysis. And if you go to the time history analysis, how earthquake should be selected and scaled, and how should we apply it? And when we want to do that, should we use the fast nonlinear time history analysis, direct integration one? And if we go for the direct integration one, which type of the damping we should use? How much the damping should be? And even there's another question is that, and there's another question is that here, do we really need to know the behind of all of that? Do we need to then know that what's the difference between response analysis or modal analysis, or even for the time history analysis, do we need to know that what's the difference between fast nonlinear time history or direct integration? And the other question is that, do we need to know that before choosing all of these, you need to know that what's the failure mechanism of the building, or just software can do it for us? There's one interesting thing is here that it doesn't matter you choose which of them and which software and which method to the analysis. At the end of that, you can find a very nice and beauty result. And it's short. I mean, the first looking of that, you see that, oh, it's stunning, it's great. It looks like more accurate if you use it more complicated analysis. But I can say that it is scary. It is dangerous more, because there is a chance that the first principle understanding of that was wrong. But because the results look like beautiful and complicated, we think that it is correct. So using the software these days is essential. We need to use it. But the question is that how we can make sure that if we are using it correctly.
Yep. So based on what Professor Pauly mentioned in his interview and what Niku just explained nicely, we want to open 3 questions to the panel and later for the audience. The first one is, as Niku said, no one can deny or question the role of computer software in today's earthquake engineering. But the question that we need to answer, to ask ourselves is that how can we, or have we equipped our engineers with the necessary knowledge and tools to, first of all, be able to properly use the software, but more importantly, verify the results and make sense out of them. And the second one, which is also somehow tied back to the first one, is I want to know what the panel thinks about these unconventional yet simple analytical methods that Professor Paulet was referring to in his interview, and several other researchers and engineers also advocate them. Could adopting such analytical methods that can provide further insight into the seismic behavior of the structures or whatever earthquake engineering is doing, help prevent or at least help minimizing the so-called misuse of computer in earthquake engineering? And the third question, which was touched by Professor Paulet at the end of his response, which is, and is something that we don't often talk about, is the role of philosophy in earthquake engineering. We have been focusing mainly on improving our technical capabilities in earthquake engineering, but have we invested enough on understanding the philosophy behind each of these techniques? We have engineers and researchers, as Niku said, that can do complex analysis or even simple ones like equivalent static or model response. But if you ask them what it is that you're doing, they may not be able to properly explain to you. Or in other words, is it even important for us, especially for our engineers, that to know the assumptions, the limitation, the philosophy behind the techniques that they're using, or it's okay as long as they know how to use the techniques, probably using a software, and most of the time get the right results. But we need to have know the expectation of the industry. Do we want them to just be an operator of certain software, as long as they know where to put the inputs and get the results? As Niku said, that most of the time they look also nice, or we want them to understand what it is that they're doing and pay more attention to the philosophy and the assumption and limitation, especially in choosing the right method to use. I hope that clarified a bit more of what this panel discussion is about. And without spending more time on that, I pass to Niku to introduce our first speaker.
Thanks. Thanks, Arsala. Our first speaker is Rob Jury. Rob is a Beca Chief Structural Engineer and works for the Beca Wellington Structural Team. He has over 40 years experience in structural design and assessment across the full range of structures in New Zealand and internationally. He has been responsible for the structural design of projects such as Sky Tower and many seismic assessment. Rob has participated in development of earthquake design standard for New Zealand, Papua New Guinea, and Nepal. He was editor of existing building assessment guidelines, and he is currently a member of Seismic Risk Working Group, delivering on how to incorporate the latest seismic hazard estimates into the design standards. He is also a member of MBIA-led Joint Committee on Seismic Assessment of Existing Building, a committee set up by MBIE to provide guidance on maintenance and update of New Zealand seismic assessment guideline, particularly in light of the change in hazard estimates, but also in response to the latest research on precast floor, Yellow C5. Rob is a member of the EQC-funded, NZSA-led Resilience Building Project, a wide range of project of work, which is having a first principles look at the society expectation and the turbo impact around the earthquake as a precursor to new seismic design processes. I just invite you up to just all yours. Thanks. I'm just stop sharing. I'm going to be one they can share. So
I will ask you.
Yeah.
Excellent. Well, good afternoon, and thanks for that introduction, Niku. Look, I started my journey as a consulting structural engineer at Beca nearly 45 years ago. And I acknowledge the role that David and Athol had in my university training. They probably didn't remember me, but they obviously had quite a part to play in terms of the way I have developed my career. When I began my engineering, I had an HP calculator. And I'd had that for 5 years, so this is now 50 years old. And it was quite sophisticated at the time. But what it signalled was I was already out of the slide rule era. And so this was a significant development for, I think, structural engineers, was the ability to have a calculator. This, of course, is reverse Polish notation calculator, which I still find the only calculator I can use. But and many of you probably won't even know what it means and what it is. So, but it certainly was latest technology of the time. In our office in Beca, we had no desktop calculators or computers for general use in the office when I joined. And they were gradually introduced from about the mid-1980s on. However, we had access to a wide range of sophisticated structural analysis computer programs, but these were mainly mainframe computing based. And I suspect for most engineering practices at the time were out of their scope of their ability to use those unless they employed somebody else to do them. It was the age of the card, and Athol and David will remember that, especially Athol. He's probably handled more cards than most of us, many of us would ever want to. At Beca, we had our own computer program for carrying out response spectrum analyses. This was interesting in the context of what I'm going to talk about. It was based on analysis of 2D frames. And if a 3D framework was required to investigate such things as torsional effects, these were assembled into a series of parallel and perpendicular frames constrained for deflection at 4 levels. Sounds a bit like ETABS, doesn't it? Well, the early versions of ETABS. But this was interesting because of the approximations made, and also the problems. For example, dealing with common corner columns, but also it was important for the insight it provided that was possible from the step-by-step procedure of putting this analysis together. First of all, you analysed the 2D frames, then you put them in, assembled them in this framework, and then you ran this, what is effectively a very simple 3D analysis for modal analysis, etc. I think the limitations were well understood and accommodated in the thinking of the time in terms of how you put it together in terms of design. Something I'd suggest is generally lost when a full 3D analysis is undertaken in today's circumstances. I would say most design engineers and analysis running 3D analyses have no idea what they're doing, what's being done and by the computer, and therefore what the results are. It's very easy now to code up 3D models. That's one advance over the years. But in putting those models together, a lot is lost in terms of what are the assumptions that you're making when you're putting those together. What are the limitations of the program you're using to deliver the analysis, especially when you get into nonlinear type analysis. So how did we do our general analysis 40 years ago? The first step was to try and minimise the analysis. That's certainly the case. I know that I made extensive use of standard member action loading formulations that you could find in the back of any text on structural analysis, and using design charts and moment distribution. I don't know whether moment distribution is taught anymore in universities. It is. Good, thanks, Brendan. But it does give you a great insight into what you're trying to do when you're doing a static analysis of a structure. I've always felt that the design charts were particularly useful because they presented a wide range of solutions on one page, and it was possible to see at a glance what was influencing the choices the designer was going to make and how adjusting the parameters might affect the solution. This insight is lost if you run a particular solution on a computer, because you only see the answer to the solution that you have analysed, unless you iterate and write everything down, which generates a design chart. You don't see that, and I think you're losing something by that sophistication. So that's one thing that I can see in terms of the so-called progress in terms of computer analysis and what the design engineer is losing. We also use techniques such as moment distribution, which I've mentioned, moment area deflection assessments, common, graphical techniques for deflections of trusses. Who would ever try to do that these days? The principles of superposition. I mean, these are three-body diagrams, method of sections, etc. These are all techniques that give you quite a lot of insight into what it is that you're getting out of a static analysis. I particularly like the MUTO, M-U-T-O analyses method, or analysis methods developed by that Japanese gentleman for the hand analysis of multi-story frames. The approach of progressively going through from story shears to column shears located at points of contraflexion in the columns, to column moments, to beam shears based on simple rules, gave a very good insight into what drives what and what would change what. So what a loss in rigidity in your the ground floor base of your ground floor columns would do to your point of contraflexion, and therefore how would it affect the moments in the column at the lower floor, and how could you control that? Because you can't necessarily prevent, although people tell me now you can, but you can't necessarily prevent the hinges forming at the base of the columns. So you can control that. So then it gives you some idea of how it affects the rest of the all of these methods are tedious in today's world, but they all give a designer an appreciation of what is affecting what, and in the modern context, an appreciation of what should be expected when the computer analyses are being carried out. And they don't have to be run right through to the full extent. I mean, a MUTO analysis, you could just be interested in the ground floor columns and getting some idea of where the point of contraflexion is. And it doesn't have to be in that first story. And you know, the Christmas tree formation of the plastic of the moments in columns is easily predicted through the MUTO process. I'm not sure that all of these things are taught in universities, Brendan. No. So moment distribution, great, I'm glad to hear that. But these other things aren't taught, and therefore something is missing, I think. If you are relying totally on the analysis, you are really missing something, I think. How many of you are really aware that over the last 50 or maybe even 60 years, Athol might correct me if I'm wrong, there's been very little development in the computer analysis techniques that are in behind the analysis programs that we currently use. They are certainly easier to use. They have better front interfaces, and they have better ways of producing the output so you can get there quicker. But what I believe has been lost is an understanding of the underlying assumptions as carried out by and the limitations that are there. And some of them are quite gross, some of these limitations. And they've always been there, but they're now lost. You probably never find them if you read the manual, if you could read the manual. Because many of these programs don't come with good manuals. Well, they come with good manuals to tell you how to code it up, but they don't come with good manuals to tell you what's going on inside the box. And just because a computer can complete an analysis does not mean that it's necessarily correct. And some programs are better than others, but ETABS does not punch out error messages when something goes wrong. It tries internally to correct it, and then you don't know where you are. So I just wonder at that. For example, most static analyses, whether carried out by hand or computer, are based on deflections being small enough that second order effects are minimized. You know, whenever we're predicting large deflections from an analysis, they are a warning that the results may not be valid and care is warranted. And I've seen lots of examples, even of recent times, where deflections have got such that there's no way the computer program result can be valid. So that's a real problem. Any structural designer should maintain a healthy skepticism over computer-generated results and be very aware of the assumptions that have been made. For example, computer analyses are very good at modelling rigid restraints as infinitely rigid. And how many restraints in real life are anywhere near that rigid in reality? The relaxation of a rigid restraint can have a significant impact on the actions within a frame. And how many people test that when they're doing the analyses, even for simple analyses? Most of what I've talked about to date is related to elastic analysis. And one comment I would make is a lot of people run elastic analyses and believe the results in them implicitly. I see this in the case of diaphragms and what have you, and try to design or assess to the peak values that are in those analyses. What is the effect of some give in the diaphragm or the structure? It reduces these peaks considerably. So we are being very conservative sometimes when we're using elastic analysis. But once plastic hinges begin to develop under lateral loads, the analyses become an order of magnitude more complicated, and the assumptions and limitations are an order of magnitude more. Although computerized analyses allow tracking of changes in stiffness as element non-linearity develops, they are much more dependent on these assumptions than elastic analyses. Near analyses. They're also an excellent way of gaining an appreciation of the effects of progressive development. Thinking about slammer analyses, they're an excellent way. I mean, they have a whole lot of limitations in themselves, but they're an excellent way of showing how development of plasticity and nonlinear behaviour in a structure affects the structural behaviour. And it's an excellent way of deciding how elements of different stiffnesses interact. And that makes it invaluable, because if you throw everything into a nonlinear computer program, you lose a total appreciation of all of that, is my experience. And it's particularly useful for those mixed systems. And another thing that I would do, which Ole was really quite adamant on, was produce those system bending moment and shear force diagrams that show how or get to some grips with how the design actions have been distributed between those systems by a single diagram that you can see at a glance. And you'll be amazed at how many problems you'll find with computer analyses and the deliberate error that you weren't aware of how it causes a problem with some of those. Computer analyses can provide a false impression of precision and accuracy, another point that was made earlier on. There are significant uncertainties in determining the response of structures to earthquake, and no structural engineer should be fully dependent on a computer-generated analysis to provide confidence of good structural performance. I think you need to use computer analyses as a tool, not a crutch. So that's really quite important, and you should have a number of things in your arsenal that tells you the behaviour that you're generating in terms of how you're modelling and what have you is correct. And you need to provide a full gambit of those techniques to provide confidence of outcomes. Of course, dealing with uncertainty is not solely limited to the analysis. Put that slide on. I presented a slide last year in a presentation I gave when I was dealing with thoughts on dealing with uncertainty. That's the next slide, is it? Just after me. Good. Just run through this. I presented this last year, probably 18 months ago, but in terms of dealing with uncertainty, and there's been a few presentations now around on this theme, around what we have to do to deal with this uncertainty, which is huge in structural engineering. I've been talking about the analysis here, but it's in all parts of what we do to create a structure. And in reality, to deal with that, we don't have to do more sophisticated analysis. What we have to do is make our structures more amenable to the seismic loads that they might get. And those top three there, I think, are the critical ones that we really need to get to grips with before we even start to think about analysis. Don't design by analysis was a critical thing I mentioned at that time, and that is where I see too often people throw everything into the model, push the button, and whatever comes out, that's what they proportion in terms of strength and ductility, if you're lucky. It might come out of that. So don't design by analysis. You will end up with a regular frame with different actions in every column. It's just not right. And the other points are just as important to think of in terms of dealing with that uncertainty. So thank you, Nikki.
Thanks, Rob. The next speaker. Sorry. Okay. The next speaker is Professor Dave Elm. Emeritus Professor Dave Elm has a long connection with the University of Canterbury, where he made a significant and lasting contribution for 40 years. Professor Elm was born in London and completed a Bachelor of Arts in Engineering at University of Cambridge. He then worked in structural dynamics at the de Havilland Aircraft Company. Dave undertook master's degree in geomechanics and a PhD on the behavior of the shell structure at Princeton University in the United States. In 1964, Dave took the role of lecturer in civil engineering at University of Canterbury. He stayed with the university throughout his career, winning the chair vacated by Professor Harry Hopkins and established a systems engineering program. He served as a dean for the School of Engineering and took a lead in the establishment of the Center of Advanced Engineering. He made notable contribution to the growth of risk-based engineering in New Zealand. Professor Elm has contributed extensively to journals on his area of expertise. He also undertook consultancy work, including for the Ministry of Work and Government projects, such as the Prime Minister's Special Committee investigating the safety of nuclear power ships. His consultancy work continued and grew following his retirement from the university in 2000. Among other things, he worked extensively on disaster recovery and related issues on the West Coast, including innovative work on improvement of infrastructure resilience. Professor Elm is a Fellow of the Royal Society of New Zealand and Distinguished Fellow of the Institute of Professional Engineering in New Zealand. He is a leader in environment thinking for engineering education and practice of civil system engineering. In 2009, he was made a member of the New Zealand Order of Merit for service to civil engineering. Just say welcome to you.
Need my PowerPoint.
Yes.
Second one here.
Yeah, wait a second. It's fine.
The next one. Yeah.
Thanks.
Kia ora, tātou. I want to talk about 3 engineering issues, but in a way, I'm just carrying on from Rob, what he said. I had no idea that he was going to say it. And also, I'm carrying on from what Tom Paulet was saying, except I don't like the use of the word philosophy. He said, you've got to not just be able to analyze and so on and so forth, you've got to be careful about the philosophy of things. I would say you might have to do sophisticated analysis, but you also have to do sophisticated thinking. And that's not being taught very well, or has not been, it wasn't in my time. It was a different sort of area. I mean, you know, just all this analysis was the exciting bit, computers and things like that. But in fact, they can lead you into all sorts of trouble, as Rob has said. So I want to talk about 3 issues, which I've come across and seem to be important. The first one is reality and models. In a way, rather than talk about being philosophical, as Tom Paulet said, I would say, look at reality as opposed to the models, because the models are not reality. In fact, everything you look at is a model in terms of how you think about things, which means that you need a specific stance to the world. It's not taught in universities, but I've written about it quite a bit, and the people that really seem to lap it up are actually practicing engineers. They say, hey, that's what we need. So Tom Paulet was right. So I'll talk about this. Reality and models and how we think can actually limit us, keep us away from reality. Okay, the second one is risk and resilience. I'll just talk about these and give you an example of how I've had to deal with a resilience problem to show you some of the issues. And thirdly, I want to talk about recovery from disasters. A recovery, this long-term thing, think of 20-year recovery in Christchurch, how it is complex, how it is costly. Recovery in Christchurch might be $40 billion, something like that. And it's neglected in terms of its research, at least in engineering. I think there's more research goes into it in sociology and law and so on. So I'm going to talk about these 3 things. First of all, reality and models. 50 years ago or so, I was spending a year in MIT, and there they were really excited about developing structural analytic models on mainframe computers. And I wandered into the office of a professor there, Mel Biggs, and Mel leaned back from his desk, covered in bits of paper, and he said, look at this, David. And he'd got drawings of the Standard Oil of Indiana building, which is one of the taller buildings in Chicago. And he said, look at this. We now know more about this building than has ever been known about a building before. I've always remembered that because that was nonsense. He knew more about the model, about this simplified analytic models. But that's how he thought. And that's the dangerous thing. Okay, let me give you an example. Here's a gravity retaining wall, very simple example. Actually, it could get quite complicated, but I won't get into the complicated detail. You got an earthquake. You want the gravity retaining wall to hold up the bank. Could be pretty big. Now, what holds that up if the Earth is accelerating is friction at the bottom of the wall, friction within the soil mass behind, and so on and so forth. You can calculate how much this friction is. But the Ministry of Works did not know what to do. They said, look, we're trying to write a code of practice for this. And trouble is, we don't know how to avoid failure. that every time we are doing our analysis, we get failure. So we put some more mass on, but the more the mass you put on the wall, the more it fails. We don't know what to do. And so I worked with a friend of mine in America, Toby Richards, about that. And what is the problem on that slide is that word failure. What the devil did they mean by failure? They thought they knew what they meant. They didn't actually know. Now, the good engineer will realize that, but it's all too easy to take ideas, words, and just say, oh, we know what it is because of familiarity. Familiarity does not mean you really understand it. Okay, well, what do? We said, oh, let's look at reality. What goes on here? Suppose you've just got what the ground is doing in an earthquake. Let's just take one pulse of an earthquake record. What happens? Here you've got the blue line gives you the acceleration of that pulse, and it results in a velocity. You integrate the acceleration, you get velocity, fine. What happens then to that wall, which is essentially like if you had a slope and you just sort of put it on the slope and you went, it would just go along like that if you shiggled it, right? So what happened was, okay, well, the wall, that gray bit, it's got a maximum friction holding it. If the acceleration pushes you beyond the ability of the friction to hold the wall against the soil and so on, it will move. And let's assume it moves because the friction is constant. It will move horizontally on that graph. The acceleration of the wall then is that gray line, and then it stops. Why? Because if you integrate the wall acceleration, it suddenly starts taking a straight line up, right? Must just go straight up because it's got a straight acceleration being integrated until the velocity of the soil and the velocity of the wall meet. So there's a difference between the two velocities, the yellow one and the orange one. And that difference, you can integrate that and get a displacement. That blue line, the wall relative displacement. Okay, you can take that, you can run through an actual earthquake trace and so on with all its ups and downs, and you can calculate that the wall will have a certain displacement. Does that displacement mean failure? No, it just moves that much, let's say, or that much, or whatever. That's what you've got to look at, the movement, not a catastrophic failure. So the result was we can calculate the relative displacement of the wall or an embankment or anything similar for any earthquake trace or collection of them, and we came up with a design approach which simply said, okay, suppose you have an earthquake typically with a maximum acceleration, maximum ground velocity, and you have certain characteristics of the soil. You can have an equation trading off the mass of the wall and the amount you allow for movement. So you design for the movement. I don't think that was picked up much in New Zealand, but certainly in Washington State, they have a lot of earthquakes up in Seattle, and they said, okay, we'll use this method. And so they do. They have a lot of freeways and big retaining walls. So the result was a new meaning of failure. What did you mean by failure? As movement going beyond a design displacement and a different design philosophy. That is more real than, it is going to fail. Okay. So that's one example of faulty thinking. Thinking you know what you mean by a perfectly familiar word, failure. Look at reality not at an assumed and inappropriate model. Okay, resilience and risk. In a way, they're kind of complementary. I worked an awful lot on risk, and risk is a wonderful sort of thing to work with, but be careful. There are three things which are wrong with it. Firstly, is that major issues sometimes are omitted. I've seen large organizations go through because despite all their work on risk management, there's something that they didn't take into account. A black swan, a thing which doesn't exist maybe, or maybe exists very rarely, came along, and that was the end of the business. So major issues are sometimes omitted. The relevant system usually, because of the complexity of good risk analyses, is represented by a severely simplified model. So watch that, the difference between the model and the reality. And risk analysis normally is confined to the likelihood and consequence of a single event. So risk models are often not complete. This is not to knock risk models. They're wonderful. They're very, very useful, but be aware of their limitations also. With regard to resilience, it is a different matter. First of all, let's say that a system is resilient if it can survive a major incident and regain its functionality, whatever it happens to be, structures, whatever, the city. Risk focuses on an incident. Resilience focuses on a system's behavior. Now, I've said there extrinsic versus intrinsic. What do I mean there? Well, in a way, the risk thing is, oh, let's look at this. There's an earthquake coming along. It's going of such and such a size. This is our structure. What's going to happen? Resilience takes the part of the structure and says, we don't know what's going to happen, but we're going to make sure we survive. So it's a very different attitude. So again, coming into that is a question of a need for a rather different way of thinking. The extrinsic and the intrinsic is the way that scientists think about it. The intrinsic is the way that good engineers look at how a building behaves. Okay, basic resilience concepts are degree of impact, what's the initial damage, and the recovery, the amount of recovery, how much it's recovered, the time it takes, because time is money, and the trajectory. So these are things which risk doesn't have with them. The recovery time is central to resilience because of the community costs very often which are involved. And for resilience, quantitative measures might not be relevant. It's much more important to understand what's going on. Okay, let me give you an example. We had this question. I was working with Ian McCann, a geotechnical engineer that many will know, and Rob Dewhurst. And the Lifelines people on the coast came along to us and said, how can we improve the resilience of our infrastructure? Now, this is a rather large ask, you know. It's 700 kilometers from the top end, right down to the Cascade River. And there are so many thousand culverts and many, many bridges and roads, communication links, power, water supplies, on and on and on. How can we improve the infrastructure resilience? Okay, we can do it. We said, a very big job. So we simplified it carefully as we could. We modeled it as 29 system elements. I don't expect you to read all those, just to say that step one is to make it handleable from an enormous thing. One of these elements might be a road plus a communication link, which goes on the road, plus this and that and the other, a multiplicity of things all at the same place. This is certainly true of bridges, of course, which don't just take vehicles over them. So we worked away at this, but how are we going to deal with the resilience issue. These people wanted to know is, what do we do to improve resilience? Well, trouble is, what's a measure of resilience? There's no really agreed measure for resilience. But anyway, we'd start with the vulnerability of something. The vulnerability of a bridge, let's say, that's one half of it. The second is the significance. The bridge might fail, but it doesn't affect anything, or it might affect the community very much indeed. So the significance and vulnerability both come into the part that piece of infrastructure is going to play. Just like a heap of dirt, if you go drive past Jackson's on the west coast, a heap of dirt comes on the way to Lake Brunner. And it's actually a stop bank to stop the often very large river, the Taramacau, going down into Lake Brunner. But the likelihood is, if you have an alpine fault earthquake, the river end is going to go up by 1.5 meters. It's going to shear through the stop bank, which is about, I'd say, maybe 300 meters from the river before it goes down its old historic path down to Lake Brunner, catastrophically. What do you do? Well, you look at the reality of it. Here you've got your stop bank. The earthquake fault trace will go through it. Well, why not just make the stop bank wider so that it doesn't actually shear right through the stop bank? There's no analysis involved there, but you've got to be aware of that thing might be quite disastrous if it happened. So that's vulnerability and significance. Then you can focus on lifelines, all these things which keep the community going. How do you handle them? Well, if you think of the major lifeline contributors to the economy of the West Coast, each is a flow. Mining, and dairy, and tourism, each of them can be characterized by a flow. What is going to hinder the flow? For how long? So that's how you look at the problem and analyze it. Here's something we produced, which was the vulnerability grading of something. We simply said it's some, whatever it is, that stop bank, somewhat vulnerable, is it very vulnerable, or what? And we're looking at a 500-year event and saying this lifeline is stopped from operating for this length of time. So that gives us a sort of feel for what you mean by vulnerability. Likewise, significance for mining and dairy and tourism, what happens? Is it going to knock things out for 8 weeks or more than 8 weeks or what? So this way we were able to come to some sort of answer. Okay, that is an example of the difficult thinking we've got to think about and the importance of the reality thinking that we've got to think about when you're dealing with a very complex, very large resilience problem. And finally, recovery. Now, I always think of the fact that after an earthquake, you've got 3 phases. The response, rescue people, the restoration, get the water supply on, and things like this, and the recovery, everything is back to a new normal. Now, there's an awful lot of work done on the response and on the restoration, done much of it myself. But the recovery, not much at all. And that's where the money is. We had a wonderful example here in Christchurch with SCIRT, the stronger Christchurch infrastructure reconstruction team. What was different about that was that it was an alliance approach. It's a management, an engineering management approach by which 3 owners, the government and NZ, Waika Kotahi now, and the city council, and 5 big contractors all got in a room. The door was locked pretty well, and they were told, come to some agreement as to how you work together collaboratively. So this was the structure of it. You had these people all contributing to the board of management, collaboratively, but it was also set up so that the contractors would work in competition as well to make their money. It worked extremely well. They had they won the gold medal of the ICE in London, and Duncan Gibb, who was heading the thing, he was asked to be the Brunel lecturer and went around the world to 30-something countries lecturing about this skirt thing. It was brilliant. Of course, all the criticisms you can make, but it was brilliant. But it was limited to infrastructure. And there were only 3 owners. Can you go beyond infrastructure to the restoration of an entire city or country? The issue is very important because I mentioned Christchurch, maybe $40 billion worth involved in the reconstruction and the recovery of Christchurch. Can it be done? We don't know. There's not enough research done. So the messages I would leave you with. First of all, there's research needed on process, on the philosophy, if you like, how we do engineering, not just press the computer buttons and things, what it should be and how we improve how we think. Risk and resilience, research is needed on resilience, understanding the metric and what you mean by good practice in resilience. And finally, recovery. Research is needed on how to do it beyond infrastructure. There's a great need. Megabucks are at issue. But people don't research on it. We need to. And that's all.
So much, Professor. What's the question? You don't know? Okay, so we will go through that. So, what's presentation? Next presentation is Craig Stevenson. Craig is a technical director of Aurecon with over 35 years experience in structural and seismic engineering. His work experience encompasses commercial, retail, residential building, and transportation infrastructure such as airport terminal facility and redevelopment and upgrade of existing building structures. He has led detailed seismic assessment and straightening upgrade for a number of key client with property portfolio across New Zealand. He provides technical and advisory assistance on seismic related aspects to other offices across the group, as well as contributing to professional engineering societies. He was member of the Loading Code Revision Committee in respect of NZS 4203/1992 and one of the study group that compiled the 2006 NZSC assessment guidelines. He was one of the contributors to the 2017 technical guidelines for the assessment of existing building and contributing author of the 2018 Yellow C5 guideline update, and past member of the CSAC and NZSC in the early 2000s. I just want to invite you to just here. Sure. I'll leave it to you. And this is all yours.
Thank you. Welcome all. I've approached this a little bit differently from the other two. Never mind. The first question that came up when we looked at understanding of structural behaviour being lost with misuse of software is, are our universities teaching the necessary material to the depth we expect and require, so we get well-rounded, technically capable graduates into our businesses, right? We know that the universities and lecturers are being challenged from the conflicting demands of growing technical content and our relevant to engineering practice today. The content the content time available for teaching, expansion of courses with non-engineering or non-technical components. We see complaints from students on the difficulty or demanding courses or exams, and we saw that last middle of the year and one of the dynamic papers when what was that, 80% failure rate? Yeah, and we obviously there's also the pressure for lecturers to secure good student feedback, to support career progression. What I did, I canvassed some of our recent graduates and come into our offices across New Zealand to see their, understand their experience with the universities. This was some of the comments. Some of the key messages here was that they felt the technical content dumped on them was excessive. They didn't have time to actually take it on board. The courses they were taking, durations were being shortened. Some of the content was being pulled from previous years. They felt it was being dumbed down. Design content for them was often limited to individual systems, and components. They had very little exposure to probably the more recent approaches on displacement-based design or processes. Their big comment was, we're focusing on passing the exams. We look at the content we think we need to know. We look at the past model exams, the past model assignments, and that's what we learn. And they say, call it a cut and paste process. More positive feedback from postgrad courses. The masters in particular, they were pretty positive. They felt they learned a lot more. They was more specific to today with all the new systems, the new approaches, and they had the time, they felt, to learn the material. And then I've canvassed, as well as my own views on this, canvassed one or two more of the senior people in our business about their perspective of the new generation of engineers entering the workforce. And again, probably the key issues here, getting a good sounding in structural engineering, the basics of structural mechanics and earthquake engineering basics. But the view is it's probably a bit narrow. It's not excessively broad. They have some general knowledge about structural systems, but there are a lot of shortcomings. Broader knowledge of overall building behaviour was lacking. The ability, in particular the ability to conceptualise and configure structural systems to a building. And they certainly had no understanding or very little knowledge about secondary structures, and of course secondary structures, things like diaphragms perhaps, but also mezzanines, roof structures and the like, and limited understanding of structural analysis methods, all the options. Postgrads, again, thumbs up, as you see. Stronger knowledge, they were getting exposed to software and other tools. They had better understanding of building behaviour. The only minor point is occasionally there's a bit of PhD bias coming into the design office about what is appropriate and why aren't we doing this, or why should we be going down this route. So what are the demands that the consultants are putting on the new generation of engineers? We're expecting increased level of technical capability. This has been driven by more demanding and detailed analysis to demonstrate compliance of design. It's really as a result of more of the recent earthquakes that have occurred and how we need to demonstrate not only the primary structural systems, we've got to demonstrate deformation or force capacity of secondary systems and the like. And part of it is being driven by the peer reviews as well. So there's a lot more effort going into designs than there were yesterday. The idea that, oh, that'll work, don't worry about it, that's gone. We're also adopting more complex and resilient building systems, low damage design and the like, and they require a lot more analysis and effort. And we are asking how young engineers get involved in detailed seismic assessments. DSAs are still a good revenue stream for a number of consultants, and we're expecting some knowledge around that, and we don't necessarily see that. Areas loading codes are an issue. We see some shortcomings. Loading codes and material standards form the basis of deemed to compliance documents for the building code, and we see a lot of designs where there are a lot of details that don't comply. Even our mid-level engineers are often unfamiliar with some of the provisions of the codes, and the documentation doesn't comply, and even sometimes peer reviews don't pick it up. And obviously there's commercial pressures. We have a commoditization of engineering design sometimes. We're looking for design efficiencies. We want to make sure we meet our budgets, our project margins. And more recently, there's been workload pressures. I think the engineering profession over the last several years have been very, very busy. And there's pressure to put work out. And a lot of our number crunching is pushed down. It's pushed down to our mid-level and junior engineers. So where has this led to, right? Increased reliance on the software tools by our engineers. And as a result, as we've seen, it's led to decreased reliance on thinking. And this is what we're seeing. Too much reliance on the black box software to achieve refined designs and efficiency in the structure. There's always a tendency for the young engineers to want to jump in, start modelling something without actually understanding what the concept is, or whether they've managed to validate it by hand calculations. And then there's a consequential belief that once they're proficient in running these software programs, they're a very good design engineer. Right? They seem to not appreciate the many crude assumptions that we have in seismic engineering. Design earthquake spectra, for example, no building ever feels the design earthquake spectra is designed for. Ground motions are quite different, right? There's all the other parameters that we use for our buildings, the section modifiers, our interfaces, our boundary interfaces, stiffnesses, spring stiffnesses, damping, soil structure interaction. It's all assumptions. It's created a culture that has turned the whole design process into an analysis exercise, rather than the analysis being a tool to support design and help verify the design. And many of the basic principles and subtleties about our modelling analysis are certainly being missed and not appreciated. And examples are when we use post-process inputs. There are not, there's a lot of assumptions made in regard to modifiers and the like. Often they don't know, they don't understand this, right? Choice of types of members. We see elements here with people put in walls and slabs, shells, structures to get the interaction. Never understood, right? Basis of moment curvature. We know what basis of moment curvature is, but there's an understanding, it covers everything, covers shear deformation, bar buckling, everything else. Well, can I say that's a load of bollocks? But that's the assumption by some people. And obviously design spreadsheet, very common. We use verified design spreadsheets. People get them, they jump into it. They actually don't know what the basis of what modelling is of the analysis. They put the input, they get the answer. So as I said, there's a loss of the broad ability to conceptualise, understand overall building or system behaviours, right, without reliance on the computer. And the self-checking process is very questionable. The issue is you don't know what you don't know, right? And as a consequence, we find we're spending a lot more time often in the formal verification process at the end of the design, trying to sort out issues which weren't picked up during the design process. So one colleague said to me, the quest for high technical capability, read that software capability, is reducing the ability of many engineers to critically review the analysis outcomes from software. I just got some examples of clangers. You can read those if you like, but the takeout out, these are ones I've seen over the last not that many years. I'm sure many of you as well have seen these sort of mistakes and errors. And sometimes your jaw drops sometimes, right? But where was the self-checking? Where was the reviews that should have picked these sort of things up? So responding more to the questions directly, how do we ensure the first principle understanding of structural behaviour is not lost, right? This is really driven by consultants. It's the compliance with the consultant's mandatory delivery methodologies and procedures. These aren't new. These are in place in most design offices. It requires formal review process right through the whole design. So we don't ensure that the black box software is not used without critical review. We're expecting our engineers to review the proposed structural system, define the expected behaviour, verify through hand calculations that it is a valid system before they start modelling, right? And we need our senior engineers over looking over their shoulder, critiquing the work, providing advice and direction, setting expectations on the self-checking, the sense checking in particular, what they're reviewing, ensuring that the output, the profiles, the moment profiles, the periods, the displacements are what we expected from the earlier work. And that this requires some hand calculations. It requires a knowledge of the assumptions as well, what was being used. Ideally, we'd like to discourage the use of software in all small types of projects, so people get back to the first principle, understand them and pick that. However, it's not always that feasible. So how do we ensure our engineers are equipped with the tools to verify software? Again, that's driven by the consultants, right? Supporting the professionals. And it depends on the process they have in place and the programs they have in place. So you'll find that many of the larger consultants do run technical sessions and in-house courses. We are aware that some of the small consultants struggle with this and the reliance more on external seminars and the like. We also look at formal accreditation processes. Should we be putting in place internally accreditation that people are competent in this sort of analysis, understand the assumptions, understand the output, and therefore it actually was one of the drivers in selection of those engineers on certain projects. Now, we also was talked about what are the tools, simple analytical tools that could be used for assessment and for design, right? Is it feasible to consider displacement-based design and the like? We know that displacement-based design is already advocated for building assessments. It's commonly used by many consultants, be it a nonlinear pushover analysis or displacement-based analysis, and it's quite a useful tool. It brings a first principle approach to it. You can actually, from the element detailing, you can determine the curve or the rotation capacity, the ductility, pretty straightforward. However, it has limitations with multi-vibration mode effects affecting behaviour. But it is quite appropriate. Whether it's appropriate for new design is the question, right? It hasn't really gained traction. I know it's only used in the transport industry in the UK and USA. I'm not sure where else it's being used. The problem is partly, I suppose, consultants are familiar with force-based design approach. The material standards are written around that. So you have detailing provisions of the material standards, which ensures that's achieved, right? How there are proposed approaches to address high mode dynamic effects. Nigel Priestley's in his displacement-based book has got an approach, and I think it also covers peak delta. But have these been adequately tested, and are they accepted? I can't comment. It really is, in some ways, it's very much a similar empirical approach, perhaps force-based design. It does provide good understanding of displacements, of stiffness and period, but it doesn't provide accelerations and the like. You end up going back to get a force distribution to use for the design. I'm happy to hear people's view on this one. So have increased technology been matched by understanding of philosophy behind these? There's been some views of that of people share with me. Some feel no. Again, it's dependent on the in-house training in the programs of the engineering consultants. We do notice that the universities generally cover well the basic principles and philosophies of structural engineering, the basics of structural mechanics. The balance of the issues that are coming out, particularly from recent learnings and autonomous systems, are left really to the consultants to address. We talk about low damage design, we talk about floor diaphragms, seismic assessments, modelling approaches. And there is support outside in the industry as well through guidelines issued through professional bodies. And there's always the learning on the job approach. So how can universities contribute? We could ensure that the courses provide greater emphasis on building concepts, overall global behaviour, response, and drive this wider lens on overall behaviour. That, according to our grads, is really missing in the courses. Look at introducing the use of some of these analytical tools to help understand the principles behind element performance, how they behave. Introduce the concepts of other types of analysis, non-linear behaviour, displacement. Also, we do know that everyone's learning a bit of static analysis at university. They do it in their last year, but there's very little knowledge around these other methods, response spectrum, non-linear time history, though. Non-linear time history is rather specialised, and we wouldn't necessarily expect people to pick up on that. And one area I always recall in my days at university, last year, we had a program where one of a senior design consultant came in and took us through, presented real-life building examples, buildings that this company had designed, and took us through how the structural solutions were adopted, why, how they're integrated into the building, the load paths, primary and secondary structural systems, and some of my mates said it was one of the best courses I've had, right? What we're saying here, we want critical thinkers coming out of our universities. So is this feasible? Given some of this may be full semester courses, not just bolt-ons. And the question is, should our undergrad courses be extended to include more content taught at master's level to seem to address some of the concerns we have about the undergrad courses? So there are other options there to help improve the capability and knowledge of engineers. And one thought is, should we be setting targeted CPD requirements for grads working in design office first 3 years? You must achieve these sort of call them diploma or whatever you want to call them. You must attend these sort of courses and gain that knowledge. Maybe that's over severe, but who knows? And then obviously there are other short courses run by universities. Maybe those should be expanded. And one thing that we do, I know at Aurecon, we provide an education assistance scheme. And we do have a number of our students going back and doing master courses over a couple of years, Auckland University and here at Canterbury University. So that's food for thought. And that's thank you.
Squeeze out. Squeeze out.
The next speaker is Professor Athol Carr. Professor Athol Carr graduated from the University of Canterbury with a Bachelor in Engineering First Class Honor in May 1964. After working as a design engineer with the Bill Lovett-Smith Consultant Engineer in Christchurch, he went to the University of California, Berkeley, and completed a Master of Science in Engineering and Structural Engineering in May 1966, and a Doctor of Philosophy in Structural Engineering in May 1967. Both degrees were under the supervision of Professor Ray Clubb. Dr. Carr joined the Department of Civil Engineering at the University of Canterbury in January 1968. Here he has pursued research and teaching interested in structural engineering with an emphasis on computer-based method of analysis, structural dynamic and infinite elements analysis. Since the early 1970s, he has been actively involved in the earthquake engineering, nonlinear dynamic analysis, and in software engineering. After 43 years teaching at the University of Canterbury, he retired in 2010 as a Professor Emeritus at University of Canterbury. He has given his course on advanced dynamic analysis in the ROSE program in Pavia, Italy from 2005 to 2018. He has developed the Rumoko dynamic analysis computer program suites over the past 40 years, and which is now used in over 130 universities, building research institutes, and consultancies around the world for research, teaching, and design analysis. Research work on the new analysis and dynamic and damping models is still taking place with graduate students at the University of Canterbury, as well as directly within Core Research Ltd.
Okay, thank you. Welcome, everybody. I feel very honoured to be here. I have to agree with some of my earlier speakers, but I'm on the side of the computer. I have been since I've been programming since 1965, so it's been a long time. It's interesting, some of the code that I'm still using goes back to the 1960s. Mathematics hasn't changed. It's still the same mathematics. Anyway, that's the minor aside. I started off in the slide rule era. I meant to bring my pocket slide rule with me, but forgot to do so. And I still have a reverse Polish notation HP calculator, which I occasionally use to check some numbers. I try to do them mentally if I can, but it doesn't always work. So let's see if I can get this to play the game now. Okay. I don't want to talk too much to the slides themselves. I want to talk to the pictures that come with them. But the question was posed, does the use of computers, has it turned the design process into a computer analysis process? I think for a lot of engineers, these young ones at the present time, yes. And that's really the wrong way of doing it. You use the computer to verify the analysis, the design you have put together. You can't do the design by computer. It's an extremely expensive, repetitive process, or maybe iterative process, and there's no guarantee of convergence. So I think you use the computer to verify your designs. The point is that a lot of our modern structures are very complex, and to try them do by hand techniques is really totally impossible. I mean, we'll talk about moment distribution. Yes, the concept's great for getting ideas across. But from a frame structure, the answers are probably within 10 to 15% of the right ones if you're lucky. And if you're not lucky and you pick the wrong material properties or try to do the wrong structure, you can be there for a long time. I found out as a young graduate engineer, 20 iterations, we still haven't got convergence. What's going on? We should have analysed it as a cantilever and be done with it, but that was not thinking. If I think about most of our modern engineering design, it's based on a whole stack of very crude, and in some cases very approximate approximations. We're still using equal displacement concept. That dates back to Newmark in 1960. The snag, if you read Newmark's paper, he says the word equal displacement. If you look at his pictures, nothing like equal displacement. The only way it's equal is they're not orders of magnitude different. But that's about the only way you can describe them as equal. But all of our codes are still using it. 60 years on, we haven't learned. Ray Clough had a paper in 1963 or 65, which says it's not true. Not picked up or not taken account of. I don't know. As I say, computer analysis is required in many cases today to verify the design that the engineers have put together. I hope not by the computer, but to make sure it actually does what you thought it was going to do. And as I say, modern structures are very complex. We have nonlinear behavior, we have base isolators, we have dampers put in them. All those things mess up the traditional simplified analysis techniques. And I'm sorry, we've got a paper coming up for the bulletin, which is actually going to pull holes in most of the analysis techniques that are used in modern design. The mathematics is wrong. So I'll leave that point at this stage. I went back to the beginnings, before computers. So we're going to take a structure. We'll go to the slides. I can talk to the slide. This is the building. This is before we had any computer analysis. Final elements of 4 slabs have been a marvel. But we had, what do? You've got slabs in 2 directions with cantilevers hung off cantilevers. It's going to be pretty stressed. We were limited, the height of the building must not exceed the height of the cathedral. So we're limited to 200mm slabs. We had to have 43mm cover to the ducts, top and bottom. Doesn't give you much room to play with. We had a 10-metre span between the columns and the tower. It's not a nice structure. Tower's off to one side. We know that's bad news to start with. But if you want the tower in the middle of the building, you can walk around it. You couldn't do much else. So it wasn't really an option. We didn't know much about, at that time, shear in what is a box. In fact, in the earthquake, the real damage was in these spandrels between the windows. The building actually could have been repaired, but the problem was you probably couldn't lease it. The building was designed with 1 toilet per floor, alternate male, female, etc. They were hoping to actually attain the adjoining site, put another tower up on the back of that one, a building on the other side, and maybe get a workable structure, but it turned out it wasn't possible. But as I say, it's a very thin slab. How did you analyse it? Well, we cut it up into strips and we worked out how much the load is going on this strip and one on the crossway strip, etc., to try and come up with an idea of what to do. And then we worked out the pre-stress to go with it. The tower was a box, not much known about torsion and boxes in those days. There's a bit of guess as to what is the torsional stiffness. Hope we got something right. I don't have the calculations anymore, so I can't check. The slabs were so thin, they would not support the weight of the curtain wall. So the curtain wall is freestanding from the ground. The floor can move up and down inside the curtain wall. The architect also wanted a wall at the back end of the building. That would have shifted the central stiffness away up to one edge. He got told in no uncertain terms what to do with that idea. There was a wall, but it's freestanding vertically and taking the load in plane was prevented from falling off the building by links, which allowed vertical and horizontal movement between the floor and the slab. But as I say, it's quite a interesting building. As I say, it predates. Which one we are? Next slide. Okay, that's the pre-stressed lift slab. It's the only really big lift slab building that's ever been built in New Zealand. You see the pre-stressing tendons in both directions. Some of them were single-ended. Return anchor to that end. But it was an interesting structure. We actually did contemplate what happened in an earthquake while they were lifting. As far as I know, the system was never set up. I wasn't in New Zealand when they actually built the building. I presume they just hoped that not end up with a lot in Worcester Street. However, that's an aside. There was no basement. All the heating, ventilating is in the roof. The foundations, we knew there was nothing solid to at least 10 metres down. One of the piles went down 7 metres on the first blow. So it's fairly soft material. Anyway, that's an example where you had to use engineering intuition because you had no tools. Engineering intuition, careful thought about what was actually going to happen. So anyway, that's an aside. Still does one. Manchester Unity. They became SBS Towers, I think that's what it was called at the time of the earthquake. Early computer analysis, St. Mary's Cathedral in San Francisco. This is a structure with 8 hyperbolic paraboloid shell forming the roof. It's a square at the bottom, it's a cruciform at the top. Each shell, as I'll show in a minute, was formed by nervy panels. Where there's a structure of double symmetry. That's what the slide up here is St. Mary's Cathedral. There's a cruciform portal frame, if you like, and there's the 8 hyperbolic paraboloids forming the roof. There was a computer analysis, finite element analysis, and the answers weren't what was expected. We spent about 3 weeks arguing about what was different, why it was different. Well, people like Professor Scordalis, Professor Rayfield, and myself, and I don't think Ray Clough was involved in this one, but trying to work out what was going on. We checked equilibrium, it was within 0.25%. And on the computers at the time, that's doing fairly well. The problem was that when you put an earthquake in this direction from left to right, we were getting tensile forces in the portal frames on the downwind side of the structure. What on earth is going on? It's not what you expected. You expected compression on this. But what was happening was this shell in here is running along this base edge on this edge. And as it's moving sideways, it's rotating about that baseline. The shell is lifting the portal frame up. And that's why you get the tension. The forces are actually coming down through the shells, not via the frame. Once we resolved that, there was a thinking process that was wrong. We were then very happy with the solution. It's the inside of the nervy panels forming the shape of the shell structures. It's a diagonal beam connecting the 2 hyperbolic paraboloids in there. The structure was that we used the double symmetry of the structure to make a simplified model. And that was again, that's the form of the nervy panels, precast concrete units covered with sprayed concrete, and then a thin concrete panel with a marble facing fixed on top. That's where the white surface comes from. But it was an interesting exercise. It was the early finite element analysis. And one of the points that I think was important at this stage, all the early finite element analyses done Berkeley or anywhere else, all the stuff for the re-entry vehicles for the NASA early spacecraft, was done by people who knew what they were doing. They were finite element people. They knew how their programs actually worked. Therefore, where were the limitations? When is it not going to work? They also knew about finite precision arithmetic. And I think that's what's missing with a lot of our modern engineers. Computers do not do exact arithmetic. And if you're not careful, you can blow your analysis out of the water. Putting dummy stiff members in, the last thing you want to do. The 2017 earthquake conference was a presentation by CSI why they're having difficulty with some analysis. They were modelling plastic hinges with very stiff members which later yield, because they had fun with the damping models. But I had to say to them, this is the most inept way of modelling a plastic hinge that I can think of. It's been after this paper was finished, they disappeared, so I don't know. I probably wasn't very popular. At that time, computer programs were very simple. Computer memory was about $1 per byte at that time. So memory was very expensive. Most computers didn't have very much. Disks weren't very well organized either. A lot of people were playing with blank tapes. The early versions of SAT had, I think, 9 tapes. Rewinds, backwinds, etc., backspacing, etc. There were no graphical user interfaces. Input data was punch cards. Output was a line printer. If you had graphical output, you usually got it some days later, because they had to be plotted, etc. And manuals, well, a bit cryptic. They wrote the program and thought, well, maybe we better have a manual. So the manual was an afterthought. What we later decided when we wrote a book on how to write programs was the first thing you actually wrote was the user manual. What are you trying to do? What information do you want? What information do you need? So you write the manual. You might have to rewrite it, but you write the manual first, then you think about writing the program. At least you get things around the right way. Go back, not too far. Misuse of engineering software. I made my comment about knowing about how the elements work, etc. One of the, we've got CTV as another example in New Zealand, but I'll leave that one aside at the moment. That really is, again, the case of people not knowing what they were doing, not understanding the model. But the best example I can think of is the Sleipner incident in 1992 in Stavanger. They built this large concrete platform. And I go back to the next slide. That's what the Sleipner platform is meant to look like. And in the process of getting the superstructure on top, they had to ballast the platform so that the bottom was at 99 meters below sea level. The platform was actually all superstructures on barges. It's a steel superstructure. They're going to float it over the top of the platform, deballast the platform so it lifts the superstructure off the barges, etc. Except they got it down. They're about to bring the superstructure over the top. There was a large bang from down below. And what had actually happened was that the failure in these tricells here had seawater in them. So you got up to 99 meters of head on the piece of shell. And 18 minutes after the first bang, the platform sank. 4 minutes later, it hit the bottom of the fjord and imploded. It was recorded as a magnitude 4 earthquake. That's how much energy was released. They converted 75,000 cubic meters of reinforced concrete structure to rubble on the seabed in 22 minutes flat. What was wrong? Well, let's have a look. This is a typical piece of example. This is the tricell is here. This is seawater. This is maybe air or some water in it. And so you've got high pressure in that wee triangle. And this is the computer model that was used, or part of the computer model that was used to analyze that tricell intersection. Now, anybody play with fun elements, it's an extremely crude model. It's also very poorly shaped elements, particularly when you think about what sort of element they are. 3D, they're probably eight node hexahedra. But the other thing was, you have to think about, that's effectively a fixed end beam with a pressure, uniform pressure on it. So what actually happens? Well, there's several things that went wrong. For a start, you have a beam with a uniform pressure. What's the shear distribution? It's linear with distances, isn't it? What they did was they looked at the results and they plotted, they used symmetry. So this point here has an image down here, and they had some values of averaging in here. They put a parabola through those three points and said, this is the shear we have to design for. If you actually look at the real piece of material and you've got this uniform pressure, what they should have had is a shear that's way up here. So they weren't thinking about it. So bad final elements, bad analysis, bad interpretation. So it's a bad thinking about checking this. The same goes for the bending moments. It's a uniform beam. You've got a WL squared upon 8, which is 212 meganewtons per meter. They again had point A and point B, which was by symmetry. Point C, then their parabola up through and computed a moment. You find that what they've got is 85% of the static moment on the system. So again, they weren't thinking. They weren't checking with what the real structure. One of my initial points that didn't show on the slide was all of our analyses are on a computer model of the structure. It is not the real structure. If you don't realize that, then heaven help us. The point is that computer model has lots of assumptions, whether it's a frame or finite element, etc. The continuity requirements are lots of assumptions. Are they realistic assumptions? Are they not realistic assumptions? Are the loadings represented the way they should be? There's all sorts of things that can go wrong. The point was that if I go back to my slide, the other point was that on the results of those analyses, the actual detailed design was also horribly inadequate. In other words, they carefully lined up all of the holes in the Swiss cheese, and the disaster was the result. The contractors, Norwegian contractors, was the biggest construction company in Norway. They found out their mistake, they redesigned, and the platform went out to the North Sea on schedule. But at the end, there were 3 people cleaning up the paperwork in the office. It had taken the total company assets to correct the mistake. So if you get it wrong, somebody's not going to be very happy. So again, that was my point that I want to get there. It's just, you have to know what you're doing and understand the modeling that you're using. And look at, how do I check? What verification techniques do I have to verify that I've got the right answers? If you don't, then you're in trouble. So, as I say, if you must understand what you're doing, you must have a good idea what solution to expect. I don't care how you get it, hopefully by some other method. Hand, crude, doesn't matter, it gets you the right ballpark. You've got to understand the limitations of what the approximations that are in your model. And if the answers are not what you expect, then one or both of those answers is wrong. And you better find out which one. That's your responsibility. Time history analyses, real fun and games. Got so many things you can do wrong. And I won't go into all the things, but you've got choice of ground motions. If you want to scale them, you can get any numbers you want. Just think about the different ways of scaling it. Which earthquakes do you pick? If you're doing time history integration, most of the implicit schemes that are in use are based on the textbook incremental equilibrium model. They do not check equilibrium. And in fact, most of them can't. If they don't compute the damping actions, you have no shot. And most programs don't compute the damping actions. Then what the damping model is. You must understand the member models, find elements, beams, curvature, whatever. Member properties, avoid dummy stiff members. You're losing in precision straight away. I think David Elms remember analysing pile dolphins for Picton Harbour, where we push on the pile dolphin that came back to meet us because we'd lost precision. Not a lot of things to do. Hysteresis models, which ones? Well, they're appropriate, etc. Mass representation, usually not a problem. Rigid diaphragms is one that's come up in the last couple of years for work that we've been doing. In some cases, we get away with it. Other cases, sorry, go back and do your design again, because in fact, rigid diaphragms are not applicable in this structure. Damping models is one of my hobby horses. Most of the software that's out there uses rally damping. Goes back to 1956. I can understand why it was used in the 1960s. Ray Clough's lecture notes talked about modal damping, but he glossed over it fairly quickly because there's no way of solving large eigenvalue problems of it. But rally damping has no physical or mathematical justification. And it leads to some highly erroneous answers. Here is one I used for the Royal Commission. All engineers would have said they had 5% damping. Well, which answers do you get? Pick a different model, you get a different answer. Modal damping is about somewhere in the middle here. But the other ones, I won't go any further. There are certain types of analyses where you have no option. This is a building that's in Jakarta, which they wanted a performance-based evaluation. That's the physical structure, and that's the Raumaka computer model was generated via ETABS, via Revit, etc., etc. And I'm sorry, the model's been turned through 180 degrees from the other mode, so I'm sorry about that. I didn't realise that until this morning. The computer model. There's this detail on the Raumaka model for the upper part of the structure, the lower part of the structure. 8,000 odd nodes, 8,000 odd members, frame members, 4,000 odd finite elements. The structure's got 33,000 degrees of freedom. You're not going to do that by hand. But nevertheless, that was the model that was set up, and that's the basic performance ASC 41 performance-based evaluations. There's the odd little bit where the designer needs to go back and have a look at the members again. And the MCE, there's a few more of them, but basically speaking, these the designers knew what the likely performance of the structure was. 16 analyses required, 8 earthquakes, 2 directions for each of those levels of analysis. We did the whole lot in 25 hours. 3 computers, 3 desktops, and that's 2013, so computers are a bit faster. Anyway, I think that's about all I've got to say. It's probably enough. We'll leave it at that. Thank you.
Scary stuff. Brilliant presentation. I would like to ask all the speakers if they can sit on the designated chairs, and can we have another round of applause for all the speakers? So we get the questions right. If anyone in here has any questions. Yep. That's when I used to see.
Just so for those online, there is Oh, sorry, maybe not.
We see the questions.
Yeah.
Cool. So we have a first question from Anonymous. What prevents New Zealand from imposing more stringent drift limits so that buildings and non-structural elements experience less damage and reoccupancy occurs earlier? So I think this is for Robin Craig, mainly for involved in codes.
You're the one who's familiar with the.
Why don't we have more strict drift limits like some of the countries like Japan has?
I think you're probably thinking of more strict limits on serviceability states, perhaps, maybe. And unless you're thinking about resilience and thinking about higher loads, higher actions, nothing. But there's nothing to stop you from putting lower limits if you need, if you don't think the code ones are correct. They are a minimum standard. So, look, I think the current limits around serviceability limit states are deliberately not well defined. They're up to the engineer to determine what's appropriate for them.
No, I think there obviously are self-imposed limits when you've got smaller structures. Sorry, there are self-imposed limits when the peak elder issues in structures. You really don't want to try and design peak buildings that don't have to. So it's quite common to pull back the drifts. So you're not captured by that one. That's a self-imposed limit.
So the second question is from Rebu. Is asking if software packages are very accessible, it opens the possibility of its misuse without proper understanding. Is it desirable to make software easy to use? Athol?
Well, I suppose I've been accused over the years of having software that's not that easy to use. However, it makes life for the user much easier if there is, say, graphical user interfaces, a bit more information about maybe choices. But if they don't understand what they're doing, whatever you do for ease of use, won't get any better answers. You still require the user to actually understand what they are doing. The problem with a lot of the modern software is, yes, they've worked a lot on the user interface to make it easy to use with nice pictures on the output. The inside engine is still the same. It's like Model A from the 1960s. So that's still a worry.
Hopefully that answers. Yep.
I mean, software, there was a discussion whether like design by software were like is discouraged and we should like focus on manually for the spreadsheet, like I mean more focused way like manually check ourselves. But the thing is that all of the softwares, like as you mentioned, most of them are not easy to access, not easy to use, not easy to access, and therefore each of them have different approach, XDM, and EM, and other approaches. And there may be more easy to use and to get the result and design based on that, but there is no like understanding on the method, on the like the approaches that they're using. That's why we're like, I mean, I think that we're mentioning that we should not rely on code and we should put the manual like design our.
That's not strictly true. You may want to do some preliminary analyses, but you can't do the final analysis till the design is actually done, because you need the design data to do the analysis properly. I think a lot of the manuals don't actually explain very well what is actually going on inside the code, so that people don't actually understand what the approximations that their analysis is actually making. And that's a matter of manual writing. Manual writing is probably more difficult than writing the code in the first place. Writing the code's moderately straightforward. writing a manual that hopefully somebody else can read is a different sort of exercise altogether. And it's often, as I say, in all the early programs, the manual was written afterwards. Was usually very cryptic and explained what the data was, but didn't do anything else. And in reality, the manual should be actually much more informative about what is actually going on.
So we have another question, anonymous. What level of experience is reasonable for graduate engineers? Not sure what that means. Should the instruction of computer-based analysis method be limited to postgraduate level?
Yeah, I'll have a go. Start with that. I'll have a go. Yeah. Look, I think there's nothing wrong with grads carrying out analysis. It's when they're left on their own to do it, and there's no overview. It's the issue, because they cannot objectively look at the results necessarily, even if they had the training in the simplified methods. They would not have the experience to undertake those checks, but the seniors who are overviewing them are theoretically responsible for the designs should be effectively looking at what they're doing and what the results they're coming up with are. And I suspect that's not happening because of the pressures in many design offices. The work is pushed down to the lowest skilled person who can do it. You're able to actually run a program. I suspect that's as far as it gets. Great, would you like to?
Look, I agree. I think you just got to realise that seismic design is a combination of experience, gut feel, intuition, good understanding of structural mechanics. You don't get that out of a graduate.
The other comment I'd make is that you do need a certain amount of expertise all the way through the design team, because it's the further you get into things, the harder it is to pick up issues. So you need to be trying to correct them. Like any quality system, you need to be correcting them as you go. You don't really pick them up. Stay on.
Do you think we need a holistic review of our industry that includes industry, Engineering New Zealand, CSOC, and the universities to I guess develop more rounded structural engineers?
Look, certainly the impression is coming down. The impression you get is actually some of the learnings yesterday losing some of their content, right? And I don't know, maybe it needs that. Maybe it's a university. So I know when we went through, the content was quite high technically. We were doing 24-hour contact time a week, right? And some of that was the design office experience, the likes of Tom. But yeah, I just got the impression, certainly working with our grads, you are trying to provide a lot more input with the hand holding, but they eventually, it's giving them the time and they will come through. But yeah, are we satisfied with our degrees? Is a 4-year degree right? Should it be a 5-year degree? But then you got to ask ourselves, do engineers get the remuneration to justify a 5-year degree? Right. I don't know what the answer is.
I think the start of the answer is probably hierarchy. Basically, each of appreciate something into the final available. Thank you. Already, society,
I would also make a comment is that after 40 odd years of teaching courses that people found hard because you had to get the right answers. But the advanced structural engineering seems to have taken a backward step in the last few years. We seem to have been told that there's a pressure to reduce the student workload. Well, the rest of the world, engineering students are expected to put in a 60-hour week, as we used to have to do, and like it or lump it if they want to be an engineer. That's still the expected performance. And the real difference in my time teaching in Italy in the Rose class was that the students would put the time in. They had a very committed requirement of 36 hours of lectures, 24 hours of tutorials, and plus homework, plus a 3-hour exam in 4 weeks. Put the pressure on them. But it's interesting, the students would finish the homework and then they'd start looking at the what ifs. It wasn't the homework, they'd start looking at the what ifs. They were so keen. We don't seem to see that amongst our undergraduates, even amongst the graduates here. It's the homework gets done at the last minute. That's the last they see.
It's a societal issue of engagement.
Yes.
And it's fine for the students. So we see us.
Comment again, when I first started working for Bill Level Smith, we put 60-hour weeks in at work. There's a time pressure on jobs that would have to be done. At least Bill paid time and a half after 40 hours.
It's not so much to learn.
Yes.
You want it.
Yeah, I've wondered how to deal with this. I mean, from a design office point of view, we're not expecting grads to come in able to run these analyses like computer games. We're not expecting them to do that. But what I would think we would expect them to be able to do is to critically review what they're doing, to ask the questions about, look, I heard this in a course at university, these methodologies of these computer programs people from the 60s, and they submit cases in terms of the framework. And do they follow the principles of physics or mathematics? Aforementioned mathematical solutions, what have you. I would be expecting to question the theory of that. It might make our senior engineers' lives bedlam in answering those questions. But I think the fact they just go ahead and run the computer programs and don't have the objectivity to think about what they're actually doing. It's a lot of the issue that I have.
Well, I don't know. I've kind of gone the whole way. I started off once upon a time as an apprentice. There's not many professors started as an apprentice, but I had to use my skills of drilling things and filing things and all sorts of things like that. Okay. Then metamorphosis, I became a kind of whiz kid mathematics, doing sort of incredibly sort of complex mathematical analyses of shell structures and so on. Or then I became a structural dynamics guy. I was head of the structural dynamics section in the de Havilland Aircraft Company. However, eventually, I began to think more and more about what you really need to do to be able to understand a complicated problem that you've really not been able to know what to do about. And the trouble is, you see, at the university, we were having to, when I was there anyway, you had to cater for two sort of customers. One wanted to have a graduate coming out, wheels spinning, you put them in a desk and design like that, with all the details, all the immediate things you had to do, which in 2, 3, 4, 5 years, you didn't need at all. The other lot said, hey, We don't want that. We'll teach people what to do immediately, but we want somebody with a very good background that they can understand. They can pick up what to do and the underlying reasons why you do it. What we didn't get much was, and I've been having feedback from people afterwards, you know, who've listened to what I've said years ago, and then they come along and they've been out in practice for 5 years or something like that, or 10 or whatever, said, wow, that was right. I do sort of crazy things like saying, okay, look, you know, you're out in the world, you're going to have to be talking to people. You're going to have to be talking to lawyers and architects and clients and all sorts of people. You better know about communication, for starters. Now, that is just one example of what I think graduating students ought to be able to do, have these sorts of skills, get out there and then move to whatever specific technique they actually need at a time. I did this because I didn't have at university when I was an undergraduate. I did not have to do anything in terms of any sort of accessible work till right at the end of the year when I had to do an exam. That was it. And so I did all sorts of messing around and learned lots and lots of things which have actually helped me as an engineer much more than the specific analytic skills and so on I learned to churn out the numbers. You can't do that now because you've got continuous assessment and students can't find these things out. How can we change that to get students better rounded? As I would see it, not just rounded just from the point of view of being just as a matter of principle, you want rounded people who really have to do the real things you have to deal with, such as I suggested, you're going to have to be able to communicate to, as I've had to do occasionally, an engine driver or something like that. And how do I go about getting the information I need with regard to accident rates and things like that? Lots and lots of different sorts of people I've had to be able to communicate with. Second one, which is rather related, is that I happen to have found that in my own engineering career, which is pretty well, probably longer than that of anyone in the room, because I think I'm quite a long way older, is somehow I've known the right people. I don't know why, but, you know, very often I've got general skills. That's why people keep coming asking me what to do. And I'll say, I don't know what to do, but then I know somebody I can work with who I can put together a solution with. Who are these people? I mean, somebody asked me, the introduction said, to find out the safety of nuclear-powered ships. I mean, what do? Go along to the American Navy and say, look, give us all your plans and specifications and so on, so we can do the analysis. No way. So what do? I pick up a phone and I say to somebody, friend in London, look, I got this problem. What do I do? Tony? And Tony says to me, well, David, if I were you, I'd give me a call because you didn't know, but I was the guy in charge of the safety cases of all nuclear-powered ships in Britain. Didn't know that, but somehow I've been able to have a series of people I know. So that's part of breadth too. Get off this sort of figures and figures and figures and figures thing to look at a broader education, which really is not broader so much as damn sight deeper and more useful. Now, one thing we haven't mentioned either is there are many pressures at the university level and within the whole international research engine, which is focusing people on fancy, bravura, mathematically based detail for engineers. We're losing this sort of deep breadth I'm talking about. How do we get it? That's the question. Nobody's asked that yet.
So
Graduates of understanding just the limits of their knowledge. Understanding the limits of the knowledge that they're getting taught here at university and they're gaining here at university, and more importantly, understanding what they don't know, understanding that, so they can then seek help, they can call for help. I think a lot of consulting engineering firms, particularly the smaller ones, haven't fully appreciated that the course content here in broad terms may have dropped from 60, expectation of 60 the other week to 40, which has meant that a big chunk of course has been dropped out. So they kind of naively, I think at least, start off thinking that the graduate they've got is the same as the graduate that might have from a previous generation, in fact, when that's not the case at all. So, and effectively, it's trying to understand thoroughly the young graduates understanding thoroughly what they don't know. And there's no shame in what they don't know because they've never been taught it. But if they fully understand what they don't know, then they can seek help from their colleagues, job, their boss. They can't be supplied for their other ways of actually filling in those knowledge gaps. For me, that's probably number one thing in terms of graduates coming out of here from an employer's perspective. Understanding what they don't know, so seek help. Thank you.
I make a comment, but I know that there's been some criticism in particular. Those particular subjects, understanding what you don't know and not doing what you don't know. And look, what I tried to explain it to our team is that this is inherent. It's an inherent gut thing that tells you that you're going beyond your competence. It's not a good enough excuse to say, well, I didn't know. As a structural engineer, you have to have an inherent gut feeling of what you don't know. Otherwise you'll do anything. And so that's what I think should be taught in ethics. I don't know what is taught in ethics here, but that's the fundamental thing, the philosophical thing about that you get that gut instinct to know what you're doing.
Next question is from David Hopkins asking, are fees for structural design enough to allow for requisite training of graduate engineers? If not, what can be done? Are the fees enough to have these type of training that you guys talk about?
Yes, there's no. I'm sorry. Yes, they are.
Yes, but it's not an excuse.
And when the current climate after the last year, ongoing.
I suppose I think they have been stay pretty steady at a level where we can operate. It's not an issue.
It's not an issue. Good to know. So the next question is structural design, arrangement, system, behavior, communication versus analysis. Is this distinction between being adequately taught, covered by conferences, etc.? Differences between design and analysis. Take care.
Which one's that?
The second one. This one. Yeah. Yeah, the top one. Chris. Comment?
Well, I think it's on the consulting practices to be educating our people on those issues. I think you do get a lot of input, not necessarily from conferences, but when we get a new system coming into play, there is a lot more guidance coming through from the technical presentations, doing quick technical seminars, approaches and guidelines being written. So that does help inform that.
I think also in our design methods at the moment, we don't have an appropriate penalty for regular and irregular structures. And we need a much bigger penalty because we know how much better regular structures perform, even if they haven't been designed for the loads that they're having to sustain. So look, if we do that, and we have that much larger penalty, maybe that's more incentive from a cost point of view to go. But many architects are quite receptive to good structural form, and it's only when we tell obviously it's this feeling that we have to deliver. We have to deliver the possible to meet every whim. And the way we typically do that is so that it works. What works means, to be honest, something else.
I'd just like to add here that there's some very, very simple ideas, at least in retrospect, we see them as very simple ideas, which are actually very, very fundamentally important. If we think about the free body diagram, for example, so simple, but trying to teach it to first-year students, they just don't get it very often. But once you've got it in your mind, deep down, it actually applies to a whole lots of different things, not just structures.
Okay, we are gonna do 2 more questions and then we will invite everyone to move to a staff club.
So really sort of an observation for comment from all of you, really. I went through University of Canterbury, been working as a practitioner for approximately 20 years. So I've seen the change from 4203 to 1170 code. A lot of buildings in Christchurch have been through the earthquake. Anecdotally, it seems to me as though low-rise buildings have become more penalised and more difficult to design, both in terms of lateral coefficient and the provision of needing to do 100+30 analyses, which pushes you towards computer modelling versus simplified Trinity area approach, which anecdotally seems to have been quite sufficient and appropriate. I just wonder whether, when you look at the buildings that have caused loss of life or near miss to loss of life, they're actually the higher rise buildings where you're into your modal analyses, and regular structures or not, perhaps there's been problems with straight lateral coefficient, resonance effects, especially in light of the new size of hazard model. And I just wonder whether we need to revisit how the codes are developing so that we can address putting more simplified engineering effort into lower risk structures, putting more loading and design effort into the higher risk structures, which seem to be having the problem with displacement compatibility and floors dropping out and things like that. Not sure if that's a question that anyone could comment on or more of a statement. Sorry.
Unsettled. It's always been a dilemma. Whether you have right margin between long period and short period structures. Short period structures. The hazard analysis pushes out a but there is that question about the short period structures and why many of them are like so that is the main issue. And then how much you should pick up the long period to cope with the fact that they have The classification is quite.
That's the difference.
Right, you must fix it. Let's get it straight.
Ah, I think that's a different issue. Totally. Well, the question is, have we got that right? Understand of classifications. Sometimes ours do look like, 50-story buildings have a population of 10 less than 10,000 people. Classified as IL2. Should it be?
When they were set, so we're talking about.
Say last question, hearing all of these, is part of the problem a disconnect between the university and the industry expectation? Could we have at least a couple of academics that can comment on that? It seems that, especially what you said, Craig, what the students have been taught at uni is not what the industry expect them to do later with them. Is it true or?
Look, without being unfair to the university, I do feel there has been a bit of relaxation on content. I almost feel that the master students are where grad students were 20, 30 years ago. I certainly do commend some quality of our master students that come through. And the extra technical content they get around, particularly around seismic systems, seismic engineering approaches. It's quite relevant today. It may not have been so relevant 20 years ago, but certainly relevant today. I think it's important those learnings come through to our issues.
Master level is the base right now.
Oh. Yes.
That's almost part of the European issue. The Norwegians used to have a 4-year, 4 to 4.5-year degree. They're now forced to have a 3 and a 5-year degree, pattern of all of Eastern Europe. The snag is what you do with a 3-year graduate degree. They're not much use for anything. The only ones that are useful are those looking to the master's degree, which is the 5-year. And my experience with the Rose School, by the time the students finish their masters in the Rose program, they were very, very competent. It was probably a bit biased because they were always selecting students.
Great. Thank you very much, everyone. I think that's one last question.
I come from America. It's $30,000. Yeah, so you're getting out with 200. Not so much here. It's
Government funding for degrees for 3-year degree and was funding for 5-year.
yeah, but you can sign additional year competency here. Getting that education, maybe missing.
Well, ASCE have talked for many years about making a 5-year degree for professional engineers. It hasn't happened here.
Very tricky subject because we have some excellent grants that come through and develop very quickly beyond people who've done masters, but then on average, probably masters on average, the masters probably down to a useful quick. And we think it's a starting period because they just set them on and get into the industry.
Just like to say that I disagree with Athol quite profoundly about this. You can keep on stuffing ideas into people for a 7-year degree or something like that. But probably within about 3 years, most of that is past history. You should be able to get everything really into 3 years. But as I kind of mentioned, there's a real problem in universities. Sorts of people who get in on staff sorts of things they think they want to teach and so on. It really needs being looked at in quite fundamental ways, what we're really trying to do.
Okay, I think we are a little bit overdue. So thank you very much. Should we thank again the speaker? Okay. We are a student chapter, so we don't have much money to get fancy wine, but
Oh, that's a
Thank you.
Thank you very much.